Greetings and salutations, my fellow math enthusiasts and students of all things mathematical. My name is Sean Spartan, and this video will be about the surreal number system. If you're not familiar with field theory or the concept of transfinite numbers, I recommend my videos on those topics. Link will be provided in the description. In a previous video, we showed that the real numbers R were a field extension of the algebraic numbers A, which in turn are a field extension of the rational numbers Q. We also extended the reals to include transfinite numbers and infinitesimals by forming the hyperreal star R. If you haven't seen that video, I'll place a link in the description. At the end of that video, I hinted at a larger field that contained the real numbers and is in fact the largest possible field to do so. These are the surreal numbers, and they are usually denoted by the symbol NO. The surreal numbers were introduced in 1969 by mathematician Dr. John Conway, and also written about in a work of fiction by Dr. Donald Knuth. The surreals include the reals, the hyperreals, all of the infinite ordinals of Georg Cantor, and the reciprocals, which are all the possible infinitesimals. The arithmetic operations that Conway defined for his number system agree with those of the real number field. Therefore, the surreals form a genuine field extension of the reals. Conway also invented his own notation for surreal numbers. A form is a set L for left and a set R for right of surreal numbers separated by a line and surrounded by braces. If the sets are lists of elements, then the braces are usually omitted. And if either L or R are empty, we usually leave a blank space. If all the elements in L are less than the elements in R, then this form represents a surreal number, which is defined as the simplest number in between, in other words, strictly greater than all elements in L and strictly less than all elements in R. What I mean by simplest will become clear after a few examples. Now, it's important to note that some surreal numbers can have more than one form. In fact, surreal numbers are the equivalency classes of the forms. This is also a property of the rational numbers, which are numbers that can be expressed as the ratio of two integers. For example, the rational number 0.5 can be expressed as 1/2, but also as 2/4, 3/6, 4/8, and so on. In fact, every rational number can be written as an infinite number of equivalent fractions. The surreal numbers have a similar property. A surreal number may be expressed by different forms. Now let's take a look at some examples of forms and their corresponding surreal numbers. If the left and right sets are both empty, we define that number to be 0. To get the positive integers, we start with 1, which is 0 on the left and empty on the right. And to get any other positive natural number n, we have 1, 2 to n on the left and empty on the right. The process for getting the negative integers is very similar, just with the left and right switched. So now we have the integers. Let's look at some non-integer numbers. The fraction 1/2 can be represented by the form 0, 1. Likewise, negative 1/2 can be represented by negative 1, 0. 1/4 is the simplest number between 0 and 1/2, and so on. Also, note that for any irrational number x, there is a form xl xr equal to x, such that xl is a strictly increasing sequence of rationals that converges to x, and xr is a strictly decreasing sequence of rationals that also converges to x. This will be important to remember later on. For example, the square root of 2 is an irrational number and is equal to 1.414213564, and etc., where this decimal expansion does not stop or repeat. This can be expressed as the form xl xr, where xl is the set 1, 1.4, 1.41, 1.414, etc., and xr is the set 2, 1.5, 1.42, 1.415, etc. These sequences of rational numbers are monotone increasing and decreasing respectively, but both converge to root 2. Another example. Pi is a transcendental number and is equal to 3.1415, etc., where this decimal expansion does not stop or repeat. This can be expressed as the form xl xr, where XL is the set 3, 3.1, 3.14, etc., and XR is the set 4, 3.2, 3.15, etc. Now these sequences of rational numbers are monotone increasing and decreasing respectively, and both converge to pi. Now I'd like to talk about the concept of birthdays. An interesting property of the surreal number system is that every surreal number has a birthday. I'm going to use the notation Sn to denote the nth day and say surreal numbers created on day Sn have birthday n. So 0 is the only number with birthday 0. On the first day, I have 1 and negative 1. On the second day, we have not only 2 and negative 2, but also 1/2 and negative 1/2 as well. On the third day, we get the fourths. On the fourth day, we get the eighths. And in general, on the nth day, we get the fractions with denominator 2 to the n minus 1, and of course the natural numbers n and negative n. There's a special name for these types of fractions. We call them the dyadic rationals, or the dyadic fractions. In other words, rational numbers that can be expressed as fractions where the denominator is a power of 2. Now you may ask yourself, when do I see 1/3? When does that come into play? When is its birthday? The answer may actually be a bit surprising. 1/3 actually comes much, much later. Now I'd like to introduce the number omega, which is the first transfinite ordinal and is the smallest number to come after all of the counting numbers or natural numbers, which are usually denoted with a capital N. For more information on omega, please see my video on ordinals, cardinals, and transfinite numbers. A link will be in the description. Now, omega is in fact a surreal number because it can be represented by the following form. Its birthday is omega, since it appears on the omegeth day. I claim that on the omegeth day, we have not only all the dyadic rationals, but all the real numbers as well. Rational, irrational, algebraic, transcendental, we have them all. To show this, I'm going to introduce the concept of the binary decimal expansion. We commonly write real numbers in base 10, where each placeholder to the left of the period indicates increasing powers of 10, and each placeholder to the right of the period represents decreasing powers of 10. For example, in base 10, the number 1, 2, 3, 4, period 5, 6, represents 1,000, 200s, 3 tens, 4 ones, 5 tenths, and 6 hundredths. And the number can actually be thought of as the sum of those terms. But there's nothing special about base 10. We could express every real number in base 8, or 5, or 16. What is going to be useful for our purposes is to consider real numbers expressed in base 2. We call base 2 binary, and every real number can be expressed as a binary decimal expansion. Now let's take a look at a typical binary number, 1101.011. Remember that in base 2, placeholders to the left of the period represent increasing powers of 2, and placeholders to the right of the period represent decreasing powers of 2. So to the left of the period, unlike base 10, where we have the ones place, the tens place, the hundreds place, etc., in base 2, we have the ones place, the twos place, the fours place, the eighths place, the 16ths place, etc. Similarly, to the right of the period, we have the halves place, the fourth place, the eighths place, etc. So our base 2 number, 1101.011, represents 1 8, 1 4, 0 2s, 1 1, 0 halves, 1 fourth, and 1 eighth. Summing this together, we get 1101.011 in base 2 is equal to 13.375 in base 10. So what does this mean, and how is this relevant to the surreal numbers? Recall that on the nth day, we have all dyadic rationals with denominator powers of n minus 1. This means that on the omegeth day, we have them all. We have all convergent sums of dyadic fractions. Since the binary decimal expansion is really just a convergent sum of dyadic fractions, and since every real number has a binary decimal expansion, we can conclude that on the omegeth day, we have all real numbers. In fact, any number that cannot be expressed as a terminating binary decimal expansion has birthday omega. This means that real numbers 1/3, root 2, e, and pi all have birthday omega. Now I'm going to show some examples of binary decimal expansions and the corresponding forms. Let's start with 1/3. Now in binary, 1/3 is equal to 0.010101, etc. on forever. This can also be expressed as the sum of 1/4 plus 1/16 plus 1/64, etc. on forever. Since the binary decimal expansion does not terminate, neither does the sum. So we know that the birthday of 1/3 is omega. To find a form to represent 1/3, I need a monotone increasing sequence of numbers less than 1/3 for the left part, and a monotone decreasing sequence of numbers greater than 1/3 for the right part that both converge to 1/3. We will use pi as our second example. Now in binary, pi is equal to 11.00100100000111111, and this number keeps going forever. This binary decimal expansion also does not terminate, but unlike 1/3, there is no repeating pattern since pi is irrational. But that doesn't really matter here. Since like 1/3, pi cannot be expressed as a finite sum of dyadic fractions, pi also has the birthday omega. As with 1/3, to find a form to represent pi, I need a monotone increasing sequence of numbers less than pi for the left set, and a monotone decreasing sequence of numbers greater than pi for the right set that both converge to pi. So far we've talked about the reals and the extremely large numbers like omega. But what about the extremely small? Recall that omega is the smallest number to come after all the counting numbers. But is there a counterpart to omega? Is there a number greater than 0 that is smaller than any positive real number? Yes, there is. We call that number epsilon, and its birthday is also omega. Epsilon can be represented by the following form, and we define epsilon times omega to be 1. In other words, epsilon is the reciprocal of omega. And we can continue on. After the omega day comes the omega plus 1, omega plus omega, omega squared, omega to the omega power, and the process continues forever until we've included all of the possible counting ordinals. At this point, we've included all of the hyperreal numbers, usually denoted star r. For more information on these numbers, please see my video on Hyperreals. A link will be provided in the description. So are we done? We have included all countable transfinite ordinal numbers. But what comes next? Well, after the countable numbers, we need to introduce a new order type. Omega 1 is the first uncountable ordinal, and it can be represented by the following form. Omega 1 has a corresponding infinitesimal, and the process just keeps going on from there. In this way, the surreal numbers contain all of Cantor's ordinals, and even inaccessible numbers if there are any. In fact, there are as many surreal numbers as there are elements in the set-theoretic universe. This is why the surreal numbers do not form a set. They are a proper class, and I really hope to discuss this further in a future video. So to visualize the sheer awesome scale of these numbers, the surreal number system is usually drawn as a tree with 0 at the root, and successive nodes are the numbers created on their respective birthdays. You can see that for the finite birthdays, the natural numbers, or counting numbers, are on the boundary, positive on the right and negative on the left, with dyadic fractions forming the inner nodes. On day omega, we have omega, all the irrational numbers, and any remaining rationals that cannot be presented as the finite sum of dyadic fractions like 1/3, for example. But we also start with the infinitesimals. In fact, surrounding every real number is an island, sometimes referred to as a monad, that contains an entire universe of infinitesimals. This alone makes the surreal number system one of the greatest inventions in modern mathematics, in my humble opinion, at least in the field of set theory. But Conway's real genius is he was able to come up with an ordering in arithmetic operations that agree with the real number subfield to show that the surreal numbers form an ordered field, and in fact, it is the largest field extension possible for the reals and hyperreal numbers. This is the ordering Conway came up with. Given any two surreal numbers x and y with their corresponding forms xl, xr for x, and yl, yr for y, we say that x is less than or equal to y if and only if every element in the left part of x is smaller than y, and every element in the right part of y is greater than x. For example, the surreal number 2 is less than or equal to omega can be demonstrated by examining their corresponding forms. For the first part of the definition, note that 0 and 1 are both less than omega. For the second part, the right set is empty, so it is vacuously true. Therefore, 2 is in fact less than or equal to omega. To show the inequality is strict, just reverse and demonstrate that omega is not less than or equal to 2. This is true since the left part of omega contains the number 3, which is not less than 2. To negate a surreal number, just switch the left and right parts of its form and negate every element in both sets. For example, we can use this definition to show that the negative of 1 is negative 1, and the negative of omega is negative omega, which is what we would expect. Now we can move on to addition. Given two surreal numbers x and y with their respective forms, we define x plus y to be the form composed on the left of x plus elements in the left set of y, and y plus elements in the left set of x, and the right part of the form to be x plus elements in the right part of y, and y plus elements in the right part of x. And for subtraction, we can use the negation we've already learned. X minus y is the same as x plus negative y. So there's no need for a separate definition for subtraction. Let's look at an example. We'll let x be omega plus 1 and y be 1. Then adding x plus y, we get omega plus 1, which is omega plus 2. Let's see if that's the answer we get using the definition provided. First, we find forms for omega plus 1 and for 1. For the left part, we add x, which is omega plus 1, to the elements in yr, which is 0, to get omega plus 1. We also add y, which is 1, to the elements of xl, which is omega, to get omega plus 1 again. Therefore, the left part of the sum is omega plus 1. For the right part, I add x to every element in yr, but yr is empty, so there's nothing to add. The same goes when adding y to the elements in xr. Since xr is empty, there is nothing to add. So the right part of our sum is just the empty set. This form represents the surreal number omega plus 2, so it worked. Multiplication is more complicated and time-consuming. I'll show the definition here. This involves multiplying pairs of surreal numbers drawn from the left and right sets of x and y to get a surreal number, then negating the result, then multiplying the surreal number form of x or y and a surreal number drawn from the left or right set of the other operand to get a surreal number, and then adding the resulting surreal numbers together. Division is usually just defined as multiplication by the multiplicative inverse. For example, x divided by y is the same as x multiplied by 1 over y or y inverse, assuming of course that y inverse is non-zero. However, in this case, y inverse is extremely complicated and time-consuming to compute. This is the formula Conway came up with for computing y inverse for any given positive surreal number y. For negatives, just compute the inverse of the corresponding positive number first, and then apply negation that we've already learned. Conway himself advised it took him over 2 years to come up with this. Now let's take a close look at an example. I'm going to let y be 3, which has the form 2 and the empty set. Now hopefully, after calculating its inverse, I get a form equivalent to 1/3. At least that's the goal. So yl is just 2, and yr is the empty set. This right away makes the calculations easier since there are none involving yr because it's empty. So I have rewritten the formula removing terms involving yr. Now according to the formula, 0 always belongs to the left part. I substitute 0 into the formula and I get 1/2 belongs to the right part. Substituting 1/2 back in, I get 1/4 belongs to the left part. Then 3/8 on the right, 5/16 on the left, and so on and so forth. This could go on forever. So for the left part, I get an increasing sequence, and I get a decreasing sequence for the right part, both of which converge to 1/3. Therefore, 3 inverse is equal to 1/3, which is what we were hoping for. So if you've been with me for my first video in this series, we showed that the rationals are the smallest field containing all the integers. We extended Q to A, the field of real algebraic numbers, and showed this is a subfield of R, the reals. Then in a subsequent video, we introduced the hyperreals as a field extension of the reals by adjoining omega to the real number line and introducing arithmetic on transfinite and infinitesimal numbers. And finally, we see that the surreal numbers form the largest field extension containing the reals and the hyperreals. If you're interested in reading more, I've provided a link to Surreal Numbers, which is a book by Donald Knuth, sold on Amazon. Just an FYI though, this is not a math text. It is a work of fiction that talks about the surreal number system. However, I enjoyed reading it, and it helped me visualize certain concepts like forms and birthdays. That's it. Thank you for watching. If you enjoyed the video, feel free to like, comment, and subscribe. If you have any questions or suggestions for future videos, please leave me a comment.